So let me just recall just briefly what we did last time, and then I'll start. So one of the things we've been doing is understanding what the mean of the random variable is, right? And then how does it, how do you, we haven't understood exactly how to play with it and what to gain from it, but we sort of define x as a discrete random variable or a continuous one. So let me go back and make this custom pen. So x is a discrete random variable. And x is from S to T. You sort of observe that E of x, the mean of x, is just going to be the sum over T and T, the chance T times the probability of x equal to T. So it's kind of the weighted average of how x distributes the probabilities onto T, and the weights being the probabilities. So this we called as the expected value of x, or sometimes I called it the average value of x, and I've used the word the mean of x, or expectation of x. So they all mean the same thing, right? So the value is going front. Then so they all mean the same thing, right? So now the issue with this one number is the following. That is, see, I'll give you 3 examples now. So now what I want to do is I'll give 3 examples. Let's say x is a random variable. X takes value 10 with probability 1. Let's take another random variable y. Y takes, let's say, 9, y is equal to 9 with probability half. And let's say 11 with probability half. And let's say take another random variable z, which let's say takes the value 0 with probability half, and 10 with probability half, 20 with probability half. Then let's go and compute E of x. What's E of x? E of x is just, x is constant random variable, so E of x is just 10. What's E of y? E of y is 9 times a half plus 11 times a half. That's again going to be 10. And E of z is also going to be 0 times a half plus 20 times a half. That's also going to be 10. Very nice. So now the crux of the matter is that all these 3 random variables have the same mean, right? So in some sense, we know that E of x is equal to E of y is equal to E of z is equal to 10. Very good. Now, let me try and tell you how to understand this. So, x is always 10. Y is sort of equidistant from 10. So, it is like sort of, I mean, in a sense, it's very close to 10 on either side. Z is a little far away from 10 on either side, but it's equally far from either side. So, somehow, they're all giving you an average of 10. So one thing I want to do is I want to somehow quantify the spread of the distribution from its average. Right? So I want to quantify how far away a random variable is typically from its average. How far away a random variable typically is from its average. So answer to this is clear from the above 2 questions. The E of z, is like average half times away, 10 times away, y is 2 away, and so on and so forth. So now the resolution of this question will be the following. So what we will do is I will convert the average or the mean of a random variable to a notion of center. Okay, that's where the random variable is standing. Okay, so you think of it as this is where random variable is standing. That its mean. That's its e of x. Okay, and then what I will do is I'll try and understand. I'll draw this line. I'll try and understand how far away should we go to capture its range. How far should we go to capture its range? So this is like what I would call as the spread of the random variable. So can we understand the spread? So for example, in the z case, it was 0 and 20. In the y case, it was 9 and 11. And the x case, it was always at 10. So try to understand spread. So one of the qualities that helps you understand spread is standard deviation and variance. Let me just add that down. This you would have seen in your 12th class, but I just want to sort of go over it probabilistically to understand properly. So definition, this is 4.2.1. Let x be a random variable with finite expected value. So this is something I've always assumed. E of x is well defined. Then the variance of random variable x is written as variance of x and is defined as expected value of the quantity. You look at how x is and how far it is from e of x. And of course now this means that it can be positive or negative. So to standardize it, you square it. That's variance of x. And the other quantity is the standard deviation of x is defined as so I think I will use the notation SD of x is given as the square root of the variance of x. So again, we have seen the well-definedness of standard deviation because note that we had seen before, if y is non-negative, then this implies that e of y is non-negative. So if you notice this quantity here in the variance, so SD is well defined. Because I am squaring x minus e of x, that's a non-negative quantity, so it's a non-negative number, so I can take the square root. It's very good. So now, so this is what the two quantities are. So let's try and see what it gives you. What do these quantities give you? So what does variance give you, and what does standard deviation give you? Let me just try and sort of play with it a bit. So variance is what? The average. I'm taking the square distance of x from its e of x, right? And then I'm looking at the average of it. Right? That's what variance of x is. So let's see. So let me write it down. So let me just let me do some observations. So what is variance of x? Variance of x is equal to, so this is a little bit more fancy of writing it. So let's say x is from s to t, right? So it's from t, and I have t minus e of x, the whole squared, times the probability x equal to t. That's what the variance is, right? Exactly. That's how I define functions of expectation of function and a variable, exactly this. You take the function that you have, which is this, and the time. This is because that is E of f of x. I've used the fact that E of f of x is the same as sum in t, f of t times probability. Very nice. So now you notice, let me put this in pink so you sort of understand what's going on. So what am I doing? I'm taking everybody in the range of t, a range of x. I'm looking at how far it deviates from E of x. I'm taking its average, right? So in a sense, variance of x is the average of square distance of x from its expected value. So now that means, how do you measure if variance of x is large? Means what? That means t minus E of x has to be large for some t. So it means that x takes with high probability, x will take a value far away from E of x. That means the variance will be large. If variance is small, that means everybody is close to E of x, and that means x is concentrated around E of x. For example, like in the previous example, if you look at this, let's do the example again. Let's go back to here. In this example, variance of x is 0, variance of y with something. Let's check that. So in our three cases, what happened? Variance of x was 0. Variance of y, x, y, and z, about it's 0. Variance of y is what now? Variance of y is, again, everything is 10. So it's 9 minus 10, the whole squared, but times a half, plus 11 minus 10, the whole squared by half. And that's going to be equal to 9 minus 10 is 1, 11 minus 10 is 1, half and half is 1. And what is variance of z now? Variance of z is 0 minus 10, the whole squared times a half, plus 20 minus 10, the whole squared times a half. And that's going to give you 100 plus 100 by 2, and that's 100. Right? Very nice. So now we have an idea now. So now variance of x is 0. So that's how tells you that the random variable is exactly at the mean. There's no difference at all. Variance of y is not so large. It's 1. That means the random variable is kind of spread. What's going on? Right. Variance of y is like 1. Right. And what happens to variance of z now? Variance of z is like 100. So it tells you some sort of something's going on. So what does it tell you? That means what are these three observations telling you is the fact that the random variables, how they are distributed away from the mean. So let me just keep this variance here. Let me just do the standard deviation as well. So standard deviation of x is 0. Standard deviation of y is 1. And standard deviation of z is 10. So again, in some sense, this is telling you, if you look at this guy, let me make it in red. In some way, it kind of compares. So x minus E of x is always 0. So that means standard deviation is 0. The range is just given by 0. In this case, somehow it's kind of exact. That is, y minus SD of y and y plus SD of y capture the range of y. And y plus z plus SD of z and z minus SD of z capture the range of z. So let me write this in a sort of a quantifiable manner. So if x has high probability of being far away from E of x, the random variable has this property, then the variance is large. Otherwise, the variance is kind of small. That's one observation. So observation one is that is to understand the spread of the random variable. The second thing is that the variance is kind of squared of the units in some sense. So if x has associated units, then since I'm squaring variance of x, say meters, right? Then variance of x has meter squared as its units. But standard deviation of x has the same units as x, so as meters as. So in some sense that this variance is a good measure of how large and standard deviation can be, but standard deviation is what one should use to understand the spread of the random variable. When it's the same units. So therefore, what one could do is the following: that let's say mu was equal to SD of x, that is the number. I just denote the symbol SD of mean of x. E of x is as mu. And let's say the idea was sigma was SD of x. Standard deviation was denoted by sigma. Then informally I'll write down or formally, one can think of the range of x to be, so what you do is you take mu, you subtract sigma, and you take mu and add sigma. So this is formally the range of x. So x will be with high probability, hopefully will be within this range. It's not exact science, but right. It's not an exact science, but this is broadly the range of x. So why do we take squared instead of absolute value deviation? We will come to in a second. So what is the role mean is playing to understand the spread of the random variable? We'll have to come to a second. So if you take absolute value in the variance of x, it may not measure the true spread. One will see that soon. I will try and illustrate an exercise that will show you that. So the squared deviation is kind of because the squared penalizes large distances far better than its absolute value. And if you want to use the absolute value as a measure of spread, then E of x is not the right quantity. Of course, this is sort of a broad idea of what the range is trying to do. So, but of course now it's the last thing you should keep in mind is that variance of x is always defined, but variance of x could be infinity, could be finite, could be a real number, or could be infinity. Okay, so it need not be finite. If variance infinity means your spread is everywhere, it's less like so going everywhere. So even though E of x is finite, the variance could be infinite. Now let me try and show you one property of variance, and then try to see if I can sort of how does one understand truly how far a random variable can be from its range. how does one use this idea of variance? Let's try and understand that. So let me call it, for lack of a better word, understanding spread. Of x from two quantities, e of x. Let me call this as mu equal to e of x, and sigma equal to standard deviation of x. So let's see now. Let's say k is a number, a natural number. Sorry, let me get back to that. K is a natural number. And let me say that I want to understand how far x is from mu. Right? So let's say x, I want to know x, I look at x minus mu, that is deviations from mean. Okay. So let's say I want to know the event, what probability the event has of, let's say, x minus mu is at least k units away from, k standard deviation units away from the mean. Okay. So I want to know what the probability of this is. What's the probability of this event? Again, suppose. So of course now, two things to keep in mind. Given PMF of x, the probability mass function of x, one can compute this explicitly, right? There's no problem. But of course, can we otherwise? The question I want to ask is, can we estimate this? Can we provide bounds for this? Can we say how large or how small things can be? It's sort of a very. I just give you mu and sigma. Can I? Like I told you that the motivation was that if I tell you x and y, mu and sigma, then I know how far the how it's some indication of the spread, because mu minus sigma plus mu plus sigma is kind of the spread. But let's try and see if how can I estimate this problem. So let's go step by step. So now, so let's see. So the event, let me call the event. The event. So let's say let me be an observant. X is a discrete random variable. Mu is equal to e of x, and sigma is equal to standard deviation of x. Right? K is some. So assume mu is finite and sigma is finite. Okay, let's assume that. I'm looking at a number k or a number k, let k be positive, and I'm trying to estimate the chance that x minus mu is at least k times sigma. So how does one do that? So now you look at the event. You look at the event x minus mu bigger than k sigma. The first thing you do is, this is the same as this event. The same as, I can square both sides, right? So same as x minus mu whole squared. So x minus mu whole squared bigger than k squared sigma squared. There's no difference. Right? Both are the same. Very good. Now you notice that let y be x minus mu whole squared. So y is a non-negative random variable. because it's a square of a quantity. Very nice. And if I take C to be equal to K squared sigma squared, C also is positive. Then, I don't know if you remember this, I said last week, I had this thing called Markov Inequality, right? I showed it to you. So Y is non-negative and Y also discrete, because X minus mu is discrete, Y minus mu is discrete. So we know that probability of Y bigger than the quantity C is less than or equal to E of Y by C. For C positive and E of Y finite is always true. Now here, what's E of Y? Here, E of Y is E of X minus mu whole square, right? X minus mu whole square. And that's just the variance of X, which is sigma squared, which is finite. So therefore, what do we have now? We have the probability of Y bigger than C. Let's call the star. Star implies, what is Y? Y is X minus mu whole squared. So X minus mu whole squared bigger than C is K squared sigma squared, right, is less than or equal to E of Y. E of Y is sigma squared divided by C. What is C? C is K squared sigma squared. Right? That's what we have shown by the above calculation. Right? So therefore, down C is K squared sigma squared. So by this is positive. So therefore, what have we shown? We have shown the chance of finding, and this event is the same as this event, X minus mu bigger than K sigma. Right? The chance of finding X, K sigma away from mu is always bounded by, here the sigma cancels off, I get 1 over K squared for all K positive. So that's a nice theorem. So here's a theorem. So I'll write theorem down. So theorem. This theorem in the book, it's 4.3.4. It's called Chebyshev's inequality. And this is the proof. Right? This is less than or equal to, what I've shown, less than or equal to 1 over K squared. It's not a strong bound, but it's a good bound. It's an initial guess. So let me just recap so I can see what's going on. What have I done? I've shown you that if I want to understand the spread of random variable, which I said was mu minus sigma mu sigma, that doesn't give you a good bound. But if I use a K here, right, this K, if I use the K, then the chance of finding it away from K sigma decays like 1 over K squared for any random variable that has a finite mean and a finite variance. Oh God, what's going on? Forget this once more. Very good. So that's one simple bound we have got. That is, probability of X away from K sigma is of the order 1 over K squared. So if K is larger and larger, you're going to get less and less probability of finding X far away from mu minus K sigma and mu plus K sigma. So it's a very useful bound. It's like a suppose I give you, let's say, K is 2. So the chance of finding X 2 standard deviation away from mu is 1 over 4. That is 0.25. So only a 25% chance that you will find X to be outside mu minus 2 sigma. So the application of this is the following. That is, from this theorem, is that if I take, let's say, K to be, 3, for example, let me make this different color. Maybe if I take K to be 3, the chance of finding x is not in mu minus 3 sigma to mu plus 3 sigma is always going to be bounded by 1 over 9. So 1 over 9 is how much? 1 over 9 is like quite small, right? It's like that. It's a small probability. So, I mean, around 10 to 15% chance of finding x outside this interval. Right? So, in some sense, this is kind of the, you can, I mean, if you're, depending on how good a probabilist you are or statistician you are, mu minus 3 sigma plus mu plus 3 sigma is kind of the range of x. After this, it's kind of small. Right. So I haven't calculating x minus mu sigma is kind of very hard to do. You'll just get 1 over k. I mean, I'm getting 1 over k squared here, right? If I took x minus mu sigma, I would just get 1 over k here. But I'm getting a better bound here, right? 1 over k squared. So the question was asked was, why didn't I just take x minus mu sigma? Why did I square it? But if I'm using the square to sort of get a better bound. Also, like if I didn't use the square, then I would not get E of y to be sigma squared. I would get E of y to be some quantity, and I'd have to know how that quantity compared with sigma, which I have not done. Very nice. So this kind of quantifies the idea of how to understand standard deviation. It's just the spread of random variable from its mean. Now, once you do this, now let's say you have your sigma, your mean mu. There is one aspect of standardization which I would like to emphasize. And I would like to do that. So one aspect of it's called standardization or standard units. So here the idea is that no matter what my x is and what my y is, or what my mu is and what my sigma is, then I'd like to sort of convert it to some standardized form. So let me just see if that makes sense to you. Let me see. So if mu is E of x, so x is a discrete random variable. Mu is E of x, and sigma is a standard deviation of x. So there are two quantities. So already we have seen that if we know that the chance of finding x outside mu minus 3 sigma and mu plus 3 sigma is kind of 1/9, right? So it's kind of standardization. So now, instead of standard units, let me call it standardization. So let's say mu and sigma are both finite. So sigma is not 0, and mu is some number. It can be 0, it's okay, but some number. So then let's look at the random variable z, which is x minus mu by sigma. Okay. So now sigma is positive, so I can consider x minus mu. Now z is also a discrete random variable. And then if I look at E of z, what's E of z going to be? E of z is going to be E of x minus mu by sigma. Right? That's the same as E of x by sigma minus mu by sigma. So x by sigma minus mu by sigma, right? Now by linearity of expectation, that's the same as 1 over sigma times E of x minus mu over sigma, right? E of x, but that's the same as that's the same as mu by sigma minus mu by sigma, which is 0. So mean of z is 0. If I scale x, if I shift x by mu, the mean of x is 0. Mean of z is 0. So then the other thing is that you notice that the variance of z is what is E of Z minus E of Z the whole squared, right? But E of Z is 0, so it's E of Z squared. What is E of Z squared? E of Z squared is E of x minus mu the whole squared divided by sigma squared. Right? That's a constant. So that'll come out of the random variable. That's going to be equal to 1 over sigma squared times E of x minus mu the whole squared. But E of x minus mu the whole squared is just the variance of x, which is sigma squared, which is 1. So this is one way to standardize a random variable. So suppose you have x is mean mu and standard deviation sigma. If you shift by x, shift by mu and scale by sigma, then you'd get variance of z is 1 and mean of z is 0. Okay, here's a question. What does it say? If we define variance of x to be x minus, then you have a weaker bound or an equal. That's right. Not 1 over k, but you'll have to compare E of mod x minus mu by sigma. You don't know how to compare that. So that's why I want to understand. I take square because I want a sort of a standard estimate of understanding how x will be outside mu minus k sigma and mu plus k sigma. It's just a calculation tool. There's nothing more than that. I know I just said 1 over k by mistake. It's just that I'll have to compare E of mod x minus mu and sigma. It's not comparable. Very good. Yes. So one thing of standardization, you can always move x by mu and divide by sigma. You'll always standardize it to variance 1 and mean 0. That's one thing to keep in mind. There's some standard properties of random variables with regard to variance and standard deviation. I'll write it down. I'll leave the proof as an exercise. It's not that hard to show because given how we have shown the properties of mean, it's kind of easy to show. So here's a theorem. Let A be a real number, X be a random variable. Such that mu is equal to E of x is finite and sigma squared is variance of x is also finite. Then, okay, the number one is first result is that if I scale x by a, the variance scales by square. That's kind of intuitively obvious because variance is square of the units, and you can easily check that. That's not a problem. We already know that the expression is linear. So mean of ax is a times mu. So variance of x will just be a squared times variance of x. The second thing is, of course, standard deviation scales the correct way. There's no problem. Standard deviation will scale exactly linearly. So standard deviation of ax is just going to be equal to a times standard deviation. That you can just get the square root on both sides and get that. The third thing is kind of interesting to understand. That is, if I shift a random variable, like you saw upstairs, if I shift x plus a, then intuitively you think a little bit. So now what happens? I'm just moving x by a, right? So I'm not doing anything. I'm just moving x by a. So its variance should not change. Its mean will move by a, but the spread should not change. So that's indeed the case. It's the same as variance of x. And the fourth quantity is again the standard deviation is the same. That's kind of obvious to understand. X plus a is the same as And these are all very trivial exercises. One can sort of see immediately. It's not the proof exercise. One can just write definition and just do this. But the intuitive understanding is clear that if I scale random variable, the variance should scale. Because if you scale random variable means the mean scales and the spread should get larger. That's what a squared times that. If a is bigger than 1. If a is less than 1, you shrink. So the proof I'll leave it exercise from definition. But what's for computationally what's interesting is another tool that you like. The tool here is the following. Let x be a random variable. For which e of x and e of x squared are both finite. Then the variance of x is given by e of x squared minus e of x the whole square. So the proof is fairly straightforward. Let me just do the proof. So we know what's the variance of x. We know the variance of x is just e of the random variable x minus ex the whole square. That's the definition of variance, right? So let me just make the inside one as purple so we can see what's going on. Right. So what happens now? Now you notice x minus e of x the whole square, right, is what? That's just x squared plus e of x the whole squared, right, minus 2x ex. Right. Now this observation you can make. So that means, therefore, variance of x, if I replace the purple part by exactly what I have, then that's going to be equal to e of x squared. Sorry, e of x squared. This whole thing, right? I'm going to replace it by green thing. So I'll replace it by e of x squared plus e of x the whole squared minus 2 times e of x. Now if you notice, e of x squared is linear. The first thing I get is e of x squared. That's easy. E of x the whole squared is a constant. That means the expectation of constant random variable is just the same thing. That's e of x the whole squared. Minus 2 comes out and I have e of x times e of x. So what have I used here? I've used the fact that in this spread, in this step, let me call this, let me put a different color for this. In this step, I use the step that e of x squared is a constant. That's what I used here, right? Very good. Now, here again, e of x is a constant, right? So, again, e of x is a constant, so I can pull it out. So, the same as e of x squared plus e of x the whole squared from the previous line, minus 2, e of x comes out, that's the green one comes out, right? The green one comes out, and I have e of x again. So if I do the algebra properly, what will I get? I just get e of x squared. E of x squared minus 2 e of x whole squared is just e of x. That's the answer.